Download this code from codegive.com, link in the description below. Efficient key recovery attack on SIDH, a deep dive with code example, simplified for educational purposes. This tutorial delves into the practical aspects of an efficient key recovery attack on SIDH, supersingular isogeny diffie-hellman key exchange. We'll cover the mathematical foundation, the attack methodology, and a simplified code example demonstrating the core principles. It's crucial to understand that this attack works on specific, and now outdated, parameter sets and variants of SIDH and is intended for educational purposes only. Disclaimer *: This tutorial aims to demonstrate cryptographic vulnerabilities for educational and research purposes. Do not use this information for malicious activities. SIDH and its successor CK, supersingular isogeny key encapsulation, have been broken, and more secure post-quantum cryptographic schemes should be used in practice. Outline * 1. Introduction to SIDH *: Briefly explain the core principles of SIDH. 2. SIDH weakness and attack overview * Describe the discovered weakness and the general strategy for the attack. 3. Mathematical foundations * Explain the key mathematical concepts like torsion points, isogenies, and the distortion map. 4. Attack algorithm * Break down the steps of the key recovery attack in detail. 5. Code example, simplified. Provide a simplified Python code example demonstrating the core concepts. 6. Practical considerations and limitations * Discuss the challenges and limitations of the attack. 7. Mitigation and alternatives * Briefly touch on the aftermath and alternative post-quantum cryptographic schemes. 1. Introduction to SIDH *: SIDH is a diffie-hellman key exchange protocol based on supersingular elliptic curve isogenies. The key idea is that Alice and Bob choose secret isogenies, apply them to a known starting curve, and publish the resulting curve. The shared secret is then derived from the final curve they both arrive at. The security of SIDH relies on the presumed difficulty of computing isogenies between two given supersingular elliptic curves. Elliptic curve * A curve defined by an equation of the form y2 equals x3 plus x plus b. SIDH uses supersingular elliptic curves. Isogeny * A non-constant morphism between two elliptic curves that maps the identity element of the first curve to the identity element of the second curve. Think of it as a special kind of function between curves. The degree of the isogeny corresponds to the size of its kernel. Kernel * The set of points that map to the identity element under the isogeny. SIDH works by Alice and Bob choosing secret isogenies with kernels generated by specific torsion points, points of a certain order on the elliptic curve. These kernels are then used to build the isogenies and publish the resulting curves. 2. SIDH weakness and attack overview *: The attack hinges on a vulnerability related to the structure of the torsion points used to define the secret isogenies. Specifically, the attack exploited the fact that the endomorphism ring of the elliptic curve, the ring of endomorphisms, which are isogenies from the curve to itself, contains non-trivial elements. The main idea behind the attack is finding distorted torsion points * identifying specific torsion points on the public curves, the curves published by Alice and Bob, that have a distorted form under certain endomorphisms. Exploiting the distorted structure * using the properties of these distorted torsion points to recover information about the secret kernels, and therefore, the secret isogenies. Recovering the secret keys * using the information gathered to efficiently reconstruct the secret isogenies that Alice and Bob used, allowing for key recovery. 3. Mathematical foundations ***. Before diving into the attack, we need to understand these key concepts. Asterisk torsion points asterisk let E be an elliptic curve and N a positive integer. A point P on E is called an N-torsion point if NP equals O, where O is the identity element, the point at infinity, on the elliptic curve. The set of all N-torsion points on E forms a group denoted by En. In SIDH, E2-A and E3-B, for appropriate A and B, play a crucial role. Asterisk isogenies and kernels asterisk an isogeny phi, E1-E2 between two elliptic curves E1 and E2 is a rational map that is a group homomorphism, it preserves the group structure of the elliptic curves. The kernel of the isogeny, denoted ker, phi, is the set of points in E1 that are mapped to the identity element in E2, ker, phi, equals P set membership symbol E1 phi, P, equals O. Crucially, if you know the kernel, you can compute the isogeny. Asterisk values formulas provide a method for constructing an isogeny phi, E-E given a finite subgroup K of E. This is essential for constructing the isogenies in SIDH and for the attack. Asterisk endomorphism ring asterisk the set of all endomorphisms, isogenies from a curve to itself, of an elliptic curve, denoted end, E. In the case of supersingular elliptic curves, the endomorphism ring is a non-commutative ring, providing a more complex structure to exploit. Asterisk distortion map, or endomorphism a special type of endomorphism on the elliptic curve. These maps distort the points in a predictable way. Finding and understanding these distortions is key to this attack. In SIDH, an endomorphism psi is used, with the property that psi, p, equals lambda p for some scalar lambda, where lambda p represents scalar multiplication of the point p by lambda. This specific type of distortion is crucial. 4. Attack algorithm, simplified. The attack can be summarized in the following steps, simplified for understanding. 1. Obtain public keys asterisk Alice and Bob exchange their public curves. Let's say Alice's public curve is E_A and Bob's is E_B. 2. Find a suitable endomorphism asterisk determine a suitable endomorphism, or a distortion map, psi on Alice's public curve E_A. This typically involves using the properties of the endomorphism ring of the curve. 3. Identify distorted torsion points asterisk compute the image of a generator of the torsion group, example E2-A, under the endomorphism psi. This gives you a distorted torsion point. Let P be a generator of E2-A and P equals psi, P, be its distorted form. 4. Check for alignment, or compatibility. The crucial step is checking whether the distorted point P is aligned with the secret kernel that Alice used to build her isogeny. This alignment check often involves computing Weil pairings or Tate pairings. 5. Recover information about the kernel asterisk the alignment or incompatibility between the distorted point and the secret kernel reveals information about the structure of the kernel. This step often involves solving a system of equations. 6. Reconstruct the secret isogeny, and key using the recovered information about the secret kernel, apply values formulas to construct an isogeny that has this kernel. This reconstructed isogeny is equivalent to Alice's secret isogeny, allowing you to derive her secret key. 5. Code example, simplified, Python with Sage Math. This is a highly simplified example using Sage Math to illustrate the core concept of finding distorted torsion points. A complete attack implementation is significantly more complex and requires optimized isogeny computation and pairing implementations. Explanation of the code asterisk. 1. Curve definition asterisk defines a supersingular elliptic curve E over a finite field Fp. Remember that this is a simplified example, real SIDH uses much larger prime fields and carefully chosen curves. 2 torsion point asterisk finds a 2 torsion point P on the curve. 3 endomorphism asterisk defines a simple endomorphism psi as scalar multiplication. In a real attack, this would be a more complex function. 4 distortion asterisk computes the distorted point P underscore prime by applying the endomorphism psi to P. 5 kernel simulation asterisk simulates a simple kernel. In a real attack, this is the secret information you're trying to recover. 6 alignment check asterisk this is the crucial, simplified part of the attack. It checks if the distorted point P underscore prime lies within the simulated kernel. A real attack would use pairings to perform a much more sophisticated alignment check to reveal information about the real kernel. 7 isogeny computation with values formulas asterisk we compute the isogeny associated to the 2 torsion point P by calling the isogeny method from SIDH math. Important notes about the code asterisk simplified asterisk this code is extremely simplified and does not represent a complete attack. It only demonstrates the concept of finding distorted torsion points and a basic, and useless, alignment check. SIDH parameters to make this a more realistic SIDH example, you would need to use the appropriate parameters for a specific SIDH parameter set, example SIKEP 434, SIKEP 503, SIKEP 751. However, those parameter sets have known vulnerabilities. Pairings the alignment check in a real attack involves using while or Tate pairings, which are more complex mathematical operations. Isogeny computation computing isogenies efficiently is a key challenge in attacking SIDH. Libraries like SAGE Math can help, but optimized implementations are needed for practical attacks. 6. Practical considerations and limitations complexity implementing a full attack is highly complex and requires deep knowledge of elliptic curve cryptography, isogeny theory, and efficient implementation techniques. Parameter selection the success of the attack depends on the specific parameter sets used for SIDH. The original SIDH parameters have been broken. Computational resources even with efficient algorithms, the attack requires significant computational resources, particularly for larger parameter sets. Implementation security care must be taken to implement the attack securely to avoid side-channel vulnerabilities that could leak information about the secret keys. 7. Mitigation and alternatives CK after the initial attacks on SIDH, CK, supersingular isogeny key encapsulation, was proposed. CK was a finalist in the NIST post-quantum cryptography standardization process. Attack on CK CK was subsequently broken by a related attack that exploited the same underlying vulnerability in the isogeny structure. Recommendation SIDH and CK are no longer considered secure and should not be used in practice. Post-quantum cryptography focus should be on secure post-quantum cryptographic schemes, such as lattice-based cryptography, example Kyber, dilithium, which are currently considered more resilient against known attacks. Conclusion This tutorial has provided a simplified overview of the efficient key recovery attack on SIDH. While the code example is rudimentary, it highlights the core principle of exploiting distorted torsion points to gain information about the secret kernels used in SIDH. The vulnerability of SIDH and CK underscores the importance of rigorous cryptographic analysis and the need to transition to more secure post-quantum cryptographic schemes. Remember that SIDH and CK are now broken and should not be used. The purpose of this explanation is solely educational.